All right, while we're waiting for these other guys, you guys remember from last week the difference between a permutation and a combination? If I took a permutation of something, A, B, C, it has to be in order. So is that the same or different than B, A, C in terms of permutations? That's different, right? They're the same combination, right? Those are the same combination of letters because combinations don't matter the order. It doesn't matter the order for combinations. It's the order that differentiates it. All right, good. What's wrong?
No, because I started lesson 6.
Oh, you started lesson 6, yeah. Yeah, it is. Well, yeah. Everybody got the email about the homework? 5? You didn't get the email about it? Do you not check your emails? I wish I had a job where I didn't have to check my emails every single minute. Do you not check your email?
I've been checking it.
Oh, all right. Well, there is an assignment 5. It wasn't up for a little while for some reason, but now it's up and should be good to go. And I'm giving you till Wednesday to complete it if you haven't already completed it by tomorrow, because I guess I screwed up. I don't know when it went away, but it was there. It was there originally and then went away, and then I had to put it back in. So I don't know what happened. All right, let's see. Who else are we waiting for? Martin? Yeah. All right, let's get going on this new stuff. So we're going to have to use combinations in a little bit for some of the stuff we're doing. So I did want you to remember that as well. The next little topic is 11.4, and it's on 11.4, and it's on the fundamentals of this thing called probability. Okay, probability is like when you're flipping a coin and you don't know what's going to happen. It's the probability of getting either a heads or a tails, let's say. Okay, probabilities are always between 0 and 1. Always between 0 and 1. In other words, you can't have a probability that's anywhere outside of that range. Okay, so if you're doing a probability problem and you get an answer like 6, you're wrong. So redo it. Okay, so try to redo it. Okay, you can also think of it as 0% probability to 100% probability. Okay, so there's where you'd get a number bigger than 1. But remember, but percentages divide by 100 to get the actual number. So between 0% and 100% is the same as saying between 0 and 1. Okay. When we talk about probabilities, we have this idea of doing an experiment. Now, you don't talk about that too often in like straight up math classes. But when you're talking probabilities, if you do an experiment, okay, what that means is any occurrence for which the outcome is uncertain. Any occurrence for which the outcome is uncertain. That's called the experiment, like when you're flipping a coin. Okay? We also have all possible outcomes. All possible outcomes. Oops. Make up the sample space. The sample space. Okay, so out of heads and tails, how many outcomes are there? 2, right? Because that's the sample space. So if we take this coin idea, okay, the sample space, SS, for a coin toss a coin, the sample space is h comma t, like that. Okay, that's the sample space because you can either have heads or tails, and there's only 2 values there. Okay? an event is a subset of the sample space. Now my board's getting a little confused here. Okay? If a coin lands heads up, well, that heads is a subset of this. It's either heads or tails, so the heads came up, so it's heads. That's a subset of the sample space. Okay? Now, to figure out the probability, for this one it's pretty darn easy, but let's do a little bit more details on this. To figure out the probability, okay, what you do, actually I'll just erase this. If you didn't get it down, you can get it in a bit. What you do to figure out the theoretical probability, in other words, what's the number that we can mathematically determine? The theoretical probability, okay, is as follows. You have S number of the sample space is the number of sample space S is the number of outcomes that you could have, the range of them can have. Okay, we call NS just the number of equally likely outcomes. Equally likely outcomes. Okay. We call NE, and this isn't going to be the biggest deal in the world. The N, don't worry too much about that, is the number of outcomes of event E. In other words, you have a certain number of total, you have a certain outcomes of that type, and it's not true for, I mean, there's only one for coins, but if you have cards and you're trying to pick like a certain suit, you've got to count all those different choices within that suit. Okay? We have the probability in this case of event E being equal to just the number of the events divided by the number of the samples total. Okay? So for a coin, if we're flipping a coin, or I guess here would be a pog, right? You have the number of, in the sample space is 2. And the number of event outcomes, if we flip a coin once, is 1. Okay? So you've got the sample space, which is heads or tails. And if we're trying to get a head, we have the event is just the head. And so we have one of those and two of those. So the probability is just 1 out of 2. Or 0.5. Does it fit within our 0 to 1? Sure it does. Okay? The probability of a coin flip coming up heads, 1/2. That stuff's not rocket science. Okay? It gets a little more tricky when you deal with things not coins. Not that tricky, really. But let me draw or do one others. Anybody go to the Kempinski and go to the casino there? What's that? Well, it's actually kind of nice out there. I mean, you know, it's a small casino. But ever been to Vegas or Atlantic City or what are the other ones? Monte Carlo? Never been there. A lot of places they have all these games are based on probability, right? One game in particular called craps is based on the probability of rolling what? Dice, right? So you can have a die. If you roll a 6-sided die, okay, if you roll a 6-sided die, what's the probability of rolling a 1 or a 2? Well, let's figure it out. Yeah, let's figure it out. Probably rolling a 1 or a 2. You can figure it out by drawing out all the cases. The sample set is just 1, 2, 3, 4, 5, 6, right? And the event in this case is either a 1 or a 2. And so the probability is just 2 divided by 6, or like a couple people said, 1/3. That's the probability of rolling a 1 or a 2. See how you can count up and figure these out pretty easily? You can't always do that, but you can do it most of the time. Okay? What's the probability of rolling a number less than 10 with one die?
Very good.
What is it?
100%.
Yeah, I've heard a lot of different answers. 100% or 1 or 6 out of 6. In this case, the event, if I'm trying to do the event for all numbers less than 10, it's the whole sample set. It's everything there. Therefore, it's 6 out of 6 or 100%. Or I guess I should just write 1 for the number there. 1. That's the probability there. Not that hard. Okay? What's the probability of rolling an even number? I don't know. Let's draw it out. 2, 4, 6. 3 out of 6 is 1/2. Stuff isn't that bad, right? Okay. All right. Dice is one. What other kinds of things do they have at casinos that you could? Cards. There we go. Cards are a big one for this sort of thing because there's lots of different ways you can ask probability questions with cards. So normally we deal with a 52 card deck. Okay, remember it's got spades, hearts, let's see, spades, hearts, diamonds, and clubs, right? Spades, hearts, diamond, and clubs. And there's 13 cards. There's 1, 2, ... to 10, and then it goes jack, queen, king, ace. Sometimes people put ace down here. Oops, there's no 1, is there? That would be the ace. 2 through 10, jack, queen, king, ace. So there's 2 through 10 is 9, 10, 11, 12, 13 different cards in each suit. OK, so we can ask lots of questions about this, right? So let's say you're drawn you are dealt a 2-card hand. Okay, 2 cards. Okay, from the deck of 52. What is the probability of getting a pair of 2s? Pair of 2s. Probability is what we're looking for. Okay. I heard, 2 out of 52 or 1 out of 13. A pair of 2s? I don't know. Let's find out. 2 out of 52 would be, well, 1 out of 13 seems a little weird because if I dealt everybody 2 cards, do you think there's 13 of you in here, one of you would have a pair of 2s?
No.
Not necessarily, right? That's probably not a little low. That's actually what? 1 out of 26? Still probably too low. Okay? Let's figure out exactly what it is. This is where we have to use combinations again. Okay. So the event, let's just figure out the event part first. In this case, the event, how many cards is each person getting, or are you getting out of the deck? You're getting 2 cards, okay? And how many 2s are there in the deck? 4. So isn't it true that we're doing 4 choose 2 for the number of 2s? Right? That makes sense? We're taking 4 of the cards that are there. We're choosing 2 of them. OK, well, if you look on your formula sheet, or if you remember this from the other day, what that is that's 4 factorial divided by 4 minus 2 factorial times 2 factorial, which is the same as 4 times 3 times 2 times 1 divided by 2 times 1 times 2 times 1. Well, 2 times 1 cancels with that one. The 4 and the 2 will cancel. 2 times 3 is 6. Okay? So there's 6 choices, 6 different combinations of getting 2 2s out of the deck. So far, so good? All right. Now, what's the sample size in this case? Okay? How many cards are you getting? Still getting 2 cards. And what's the total number of cards that you're choosing from? 52. So isn't it true that we're doing 52, choose 2? That's the sample size, the total. Right? In this case, 52 factorial divided by 52 minus 2 factorial times 2 factorial, which in this case is 52 times 51 times 50 times, let's see, that's actually what, 50? Sorry, I lied. There we go. 52 times 51 divided by 2 times 1, which is what? 1326. Okay? Number of the event, number of ways we can do the event, number of ways total, 6 out of 1,326. You can actually divide 6 into 1326, and it's 1 out of 221 is your probability. It's actually pretty small probability to get a pair of 2s. I mean, you know, you start dealing yourself a card, shuffle, deal 2. 2 2s, nope, try again. Deal 2, try again, right? The odds are, that's a slightly different topic. Probabilistically speaking, it will take you roughly 221 times before you get a pair of 2s. If you're just a deal them, reshuffle, deal them, reshuffle. Okay? That's a whole other topic altogether, which we'll get to later, about what it means to say, on average, we have 221 tries before to do it. But that's the way it works. Okay? All right. Let's try another one. This one's actually a little more tricky too. People still writing this one down? Good. Okay. Let's say instead of a pair of 2s, you want to get a full house. Not a full hose. I'm going to get a full house. All right. You want to get a full house. What is a full house in poker? 3 of a kind. And you also got to have 2 of a kind, or a pair. And that's your whole hand, is those 5 cards makes up your total. Okay? All right. So let's figure this one out. In the event, let's do the 3 of a kind, adding up the 3 of a kind first. Okay? All right. How many cards are you going to choose to make that 3 of a kind? Okay? There's going to be 3 cards. Now, how many are you choosing from? This is where it gets a little odd. This is where it gets a little bit tricky. If you have like 4, 4, 4, how many cards are there to choose from to make 3 4s? There's only 4 cards that you can make 3 4s. Well, hold on. It's not even 13. How many 4s are there in the deck? There's 4. So it's going to be 4 choose 3 for each different number in the deck. How many did we say there were? 13. So in this case, you're going to do 4 choose 3 times 13. And that's how many choices we can do. Okay, there's 13 different ways to choose 3 cards from the 4 that you can choose for an individual card. I know. This one's a little tricky. Okay? But that's only for the 3 of a kind. And by the way, we're multiplying these together because every time you add some other part like this, you have to multiply it together. Okay? How about the 2 of a kind? Can we do the same thing for that? How many cards are you choosing now? 2. I'm going to put it over there. How many do you have to choose from to make those 2? 4. How many cards are there to choose from?
26, 13, 14.
You'd think it would be 13. If you're 26, no. It's not 26. How many cards can you choose a pair from? If you want a pair of 3s, how many different cards can you choose those pair of 3s from? There's only 4, right? 4 choose 2. A bunch of you said, oh, well, there's 13 to choose from. Well, guess what? We can't choose the one we already chose. In other words, you can't make a full house with 4, 4, 4 and then 4, 4. You can't do it because there's not enough 4s in the deck unless you got some sort of wild cards or 2 decks or something. Casino games, generally they use more than 1 deck. Although you can go to some casinos where they have 1 single deck poker, which is kind of cool. But anyway, a lot of times they'll have more than 1 deck in there, so this is not necessarily true, but it's not a 52 card deck. It's a 104 card deck or a 500 and something card deck. Okay, so it's not going to be times 13. It's going to be times how many different numbers are there left over? 12. Okay? 4 choose 3 times 13 times 4 choose 2 times 12, okay, is the same as saying, I'll rearrange this a little, 13 times 4 factorial over 1 factorial times 3 factorial times 12 times 4 factorial over 2 factorial times 2 factorial. Okay? Should be a 4. Why 12? The first thing we're doing is picking the 3 of a kind. Okay? We're picking the 3 of a kind, and how many different choices were there how many numbers are there to choose from? Let's say you're really lucky and you get 3 aces. Okay? So now your hand looks like this. Ace, ace, ace. For the pair, can we do more aces? No. So how many different numbers do we have to choose from? Only 12 now. So that's where the 12 comes into play. Okay? Anyway, if you do this out, you get 30,744. Is that what somebody said? Yeah? OK, 3,744. And what is the sample space in this case? How many cards are you choosing for your hand? 5 cards out of how many? 52. 52, choose 5. 52 factorial divided by 52 minus 5 factorial times 5 factorial, as it turns out, is 2,598,960. Pretty big number when you do that all out. Okay? 2,500. So the probability of getting a full house is 3,744 divided by 2,598,960. Okay? Which, if you divide that out in your calculator, is about 0.00144, or about 1/10 of 1%, or 0.14%. Is there any, does it now make sense why a full house beats a pair? Because it's much harder to get a full house than it was to get a pair. Okay, so when the rules of poker are strictly based on these probabilities. If you went and figured out how hard it is to get a straight flush, which is the hardest one to get, you're going to get a really, really tiny number. You only get that very, very infrequently, but it beats all the other hands. Okay, so you can figure some of those out too. If you are a gambler, and if you want to become a gambler, or if you want to become a gambler, you need to know how to do this stuff, right? And a lot of gamblers know how to do a lot of this stuff in their heads. They've seen this stuff a lot. They know this stuff really, really well because they need to know whether to bet or not. If they know what's in their hand and they see what's like for, what is it, Texas Hold'em or whatever, where you see some of the cards on the table already, right? You need to know what the odds are or what the probability is of winning your hand versus what you've got and what you think the other guy's got. So it's, it's really important if you're going to go into a world of gambling. Not that this class is trying to teach you how to be gamblers, but it is kind of, it is kind of interesting stuff. Okay? Any questions on that? We'll do more examples about that a little bit later. Okay? All right. So that's a little bit about probability. And again, we'll do a lot more examples in a bit. Okay? The next section, that was actually the section. The next section is 11.6, which is events including not and or. And we'll see what that means. And we're also going to talk a little bit about odds. Okay, like if you're horse racing. Because normally they don't talk about probabilities when they're doing horse racing. They talk about the odds of winning something versus the probability of winning something. Okay? All right. If we roll a die, okay, we roll a regular old die. Okay? If we roll a die, the event is defined as roll a 1, let's say. Okay, let's say that we are defining an event as roll a 1. Okay. When we say not E, what do you think we mean? Not 1, in the case of rolling a die, is what? Roll a 2, 3, 4, 5, or 6. We have some rules that we can deal with this. It's actually pretty simple rules. The probability of an event equals 1 minus the probability of not that event. Okay? In other words, let's just do this example. For a die, if you want to roll a 1, what's the probability? 1 out of 6. If you want to roll not a 1, how many out of 6 is it? 5 out of 6. What is 1 minus 1 out of 6? That equals 6 out of 6 minus 1 out of 6, which is 5 out of 6. It always works that way. If you know what the probability is to get a number and you want to find not E, much, much easier by just subtract it from 1. Okay? It gets harder or it gets more important to know this rule when you do things like a deck of cards. Find the probability that you are not dealt a heart out of a deck of cards. Okay? 52 card deck, not a heart. Okay? Well, if we say that the event is dealt a heart, okay, and that's going to be, how many different ways can you be dealt a heart? 13. Okay. The sample space in this case is still 52 because there's 52 cards. Okay. Well, the probability of not a heart equals 1 minus the probability of a heart. Therefore, it's 1 minus, well, the probability of a heart is 13 out of 52, which is going to be 52 out of 52 minus 13 out of 52, which is what? 39 out of 52. And for homework, you're going to have to reduce those, I think, when you do the homework. And this is going to be 3/4. Okay? Probability of picking a heart, 1/4. Probability of not picking a heart, 3/4. Okay. Let me see. I had one other thing I wanted to show you. If I missed it. One thing I did miss. Hang on. We can sometimes figure out the probabilities by doing experiments like in real life. Okay? So let's say you flip a coin 10 times. Okay? Flip a coin 10 times. Let's actually try. Anybody have a pog or a coin? I wonder if I have a pog. I don't think I have a pog. You got one? All right. Flip it. Can you tell heads from tails on that one?
Sure.
OK. Go ahead. Flip it once. What'd you get?
Tails.
Tails. Do it again.
Tails.
OK, do it again.
Heads.
OK, do it again.
Tails.
Uh-huh. 6 more times.
Tails.
Uh-huh.
Heads.
OK.
Heads.
OK.
Tails.
OK. 2 more times.
Tails.
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 Tails. OK. The empirical probability, in other words, the experimental probability of doing this is going to be out of 10, we had how many heads? 1, 2, 3 out of 10 equals 0.3, which is the experimental probability of getting a head. So what's the experimental probability in this case getting a tail? It's not head, so it's actually 7 out of 10, or you could count up 7 out of 10, 0.7. If you were to keep doing that all night, if I said, now do this 1,000 times, you would probably start getting closer to 0.5, because this is a pretty small sample. Okay, pretty small sample size. So it's 0.3 and 0.7. Or it could be a POG weighted, if it's weighted weird, and tends to come up tails more often than heads, but I doubt it. It's probably just that he didn't do enough experiments to get it. But you can take an empirical probability by actually doing an experiment. Okay, and that's the way, that's the way you can sometimes, get probabilities for things that you don't know the actual math behind. Okay, but we're not going to see too much more of that. Okay, on page 637 in your book, I'm going to draw this as fast as I can. There's a pie chart. Okay, pie chart looks like this, and I apologize if I get let me get the middle right at least. Okay, like that, and then there's one like that, and then there's one like that, and then there's another relatively big one, and then there's a smaller one, and then an even smaller one, and then an even smaller one, and then the other one. I think that's right. Okay, I'm going to just write the millions in here. 9 million, 33 million, 40 million, 40 million, 31 million. Let's see, 19 million, 13 million, and 6 million. And this is greater than or equal to 80, less than or equal to 19, 20 to 29, 30 to 39, 40 to 49, 50 to 59, 60 to 69, 70 to 79, and less than or equal to 80. Any idea what this represents? These are ages on the outside. And on the inside, it's the number of US car drivers. Number of US car drivers. So in other words, 9 million car drivers out there are less than 19, which should scare you a little bit, because remember when you were 19 and you were a crazy driver. Okay? 6 million are greater than 80. That should probably also scare you, right? Because older drivers tend to be a little bit reckless. My grandfather lived to be 90, I guess 91 or 92 years old, and he was driving almost all the way until the day he died. And when he was about 89, he got in a few accidents here and there, and stuff that was his fault. Nobody was hurt, he was hurt a little, but not terrible. But my dad and my uncle decided they were going to make him take a driving test, and if he failed the driving test, they were going to be like, sorry, we're taking your license. And he's like, fine, aced the driving test. Absolutely aced it, right? And they're like, all right, you can keep driving, but he still got in a couple accidents. But anyway, okay. So here's a chart, right, that lists all the driving ages. Okay. What is the probability that a randomly chosen driver is not in the 50 to 59-year-old group? So here's the 50 to 59-year-old group, like this. What is the probability, if you were to throw a dart at this chart, you would hit somebody who's not in the 50 to 59-year-old group? Okay? Well, I'll add this up for you. First of all, there's 191 million, million people. The other millions that aren't on here are not drivers, I guess. Okay? So 191 million people there in the graph. The probability of not 50 to 59. What's the easiest way to do this? Yeah, it's going to be the probability of all the rest. Well, it's going to be the probability is 1 minus the probability that it is somebody 50 to 59. Right? So it's going to be 1 minus, well, this is easy, 31 divided by 191. First do the 31 divided by 191, then you subtract that from 1. And you end up with either, well, 191 minus 191 over 191 minus 31. It gives you, let's see, 160 divided by 191. And then you can reduce that if you want to. Okay? But that's the easy way to doing that. So instead of adding all the other pieces up, and then, so you could do that. If you added this one and this one, this one, this one, this one, this one, and divided by 191, you'd get the same answer. Okay? As 160 divided by 191. Okay? All right. Now, any questions on the pie chart? Okay. Sometimes we have events that can occur simultaneously. Okay? In other words, and we have events that cannot occur simultaneously. Okay? So let's say you were to draw a card from a deck, and you were to say, what's the probability of drawing a face card, in other words, Jack, Queen, King, Ace, or a 2? Can both of those things happen at this? Can you draw a 2 that's also a face card? No. Okay? So those two events are called mutually exclusive events. Mutually exclusive events. The nice thing about mutually exclusive events is that to find the probability of A or B, given A or B as your events, right? That's just equal to the probability of A plus the probability of B. For our example, if you want to look at the probability of a face card or a 2, okay, well, how many different face cards are there? Well, let's see. There's Jack, Queen, King, Ace, right? There's 4 in each suit, and how many suits are there? Hang on, I don't think this is right. Hold on.
Ace is not face
Yeah.
card.
Oh, Ace isn't considered a face card?
No.
Oh, I guess it's not because it doesn't have a face. So 3. Sorry, 3. So in other words, Jack, Queen, or King. Okay, 3. And how many suits? 4. So you've got 12. It's funny, I always thought Ace was a face card. I guess it isn't. Well, anyway, 12 out of how many total cards? 52. Okay, how many are 2s in the deck? 4 out of 52. Well, because they are mutually exclusive, you can't be both a face card and a 2, you can just add these together to give yourself a probability of 16 out of 52. Because really, it's like saying a face card plus one other card, which isn't a face card. So there's a total of 4 per suit, which 4 times 4 is 16. So 16 out of 52. Okay, if you reduce this, that's 4 out of 13. Okay? However, if these events are not mutually exclusive, okay, give me an example of not mutually exclusive in this case. Face card or what? No, face card is a jack, so that's not good. Face card or even number? That's probably, although face cards, can they be even?
Same suit.
How about same suit? That's a good one. Face card or the same suit. Well, now you're kind of doubling up on some, because some face cards also are of some suit. Not same suit, but let's say face card or heart, something like that. Okay? In this case, we have if they are not mutually exclusive, okay? We now have to do the following. We have to take the probability of A plus the probability of B, just like before, but we have to subtract out those extra cases, which in this case is the probability of A and B. And I'll show you how to do that. Okay, what you do, remember, you're looking at the 2 that you are looking for minus all those overlap cases, if you're trying to figure that out. Okay, so here we go, a heart or a 2. Probability of a heart or a 2. Okay. What's the probability of a heart? How many hearts are there in the deck? 13 out of how many? 52. The probability of a 2, what did we say that was already? 4 out of 52. Okay. The probability of a 2 and a heart. How many 2 of hearts are there? Probability of 2 and a heart is going to be 1 out of 52. So do you see how we're going to now apply this? It's going to be 13 out of 52 plus 4 out of 52 minus 1 out of 52. 13 plus 4 minus 1 is 13 plus 3, so it's 16 out of 52. Okay, which if you reduce it is 4 out of 13. So you're just saying, look, sometimes we have an overlap there. If it's an overlap, you can't count it in the whole probability thing, so you get rid of it. Questions on that? OK. Let's do this. Let's take a little break. Again, I know it wasn't that long between breaks, but I see some eyeballs rolling back in their heads. So let's take a break, come back in about 10 minutes, 10 after 7. All right, the next thing we're going to talk about is odds. Okay, and odds, I was always confused about odds, like with horse racing and stuff, because they have like, oh, somebody's 8-to-1 odds and 3-to-2 odds and all that. We're going to figure all that out. Okay, if the probability of an event is, if the probability is P of E, probability of an event, just like we've been doing, probability of an event. The probability is P of E, okay? The odds in favor, then, the odds in favor of the event, okay, are found by the following, okay? The probability of the event, which you've already got, divided by the probability of not the event. That's not so hard, is it? The odds, not the ODSS, the ODDS, the odds against E, okay, is the probability of not E divided by the probability of E. Also not very hard. Okay. What did we say the probability of E equals in terms of not E? Probability of E equals what? We did it right before the break. In terms of not E, 1 minus probability of not E. If you add not E to both sides, you get the probability of E plus the probability of not E equal to what? 1. So if you notice, in both of these cases, the odds calculations, the numerator plus the denominator equals 1. Okay? So that's nice to know. The probability of the top plus the probability of the event plus probability of not the event is equal to this total sample size that we're talking about. Okay. Let's do an example. Draw a card from a 52-card deck. I'll do the example right here. 52-card deck, 1 card. What are the odds in favor and the odds against drawing a heart? Odds in favor and odds against drawing a heart. Okay. The odds in favor of drawing a heart. Okay. What is the probability of drawing a heart? 13 out of 52. Okay? That's the probability of drawing a heart. What's the probability of not drawing a heart? It's 1 minus that, or 52 minus 13, which is 39 out of 52. If you take this divided by this for the odds in favor, you get 13 out of 52 divided by 39 out of 52. If you flip this and multiply, the 52s are actually going to cancel out, and you're going to get 13 out of 52. The odds are 39. Sorry, thank you. 13 out of 39. 13 to 39 are your odds in favor of, hey, right? What's that? 1. Yeah, 1/3, or one. You normally do. You also see it like this: 1 to 3. So the odds are 1 to 3 in favor of you getting a heart, meaning you're not that likely. 3 times you're going to get something else. 1 time you're going to get your heart. Okay, if you're like randomly picking. Okay. How about the odds in favor of getting a queen? Odds in favor of getting a queen, okay, for a queen. Okay, what's the probability of getting a queen? 4 out of 52. The probability of not getting a queen is going to be 48 out of 52. So the odds in favor of getting a queen, 4 out of 48. Divide those two, you get 4 out of 48, or 1 out of 12. Okay? Or 1 to 12, or 1 to 12 in favor of getting a queen. Okay. What are the odds against getting a queen? 12 to 1. 12 to 1 against getting a queen. Okay. So when they say that there's a certain horse and the odds are 8 to 1 in favor of that horse, do you want to bet on it or not? You absolutely do, right? Because they're telling you that it's pretty darn good shot that the horse is going to win. 8 times in the track they predict the horse is going to win. 1 time the horse is not. Now if it says the odds against a win are 8 to 1, no. You don't want to do that, right? If they say the odds in favor are 1 to 3, how about the odds in favor of 2 to 5? Good odds or bad odds, relatively speaking? Well, 2 to 5 means 2 times you're going to win, 5 times you're going to lose. So, a little less than 50%. Probably wouldn't want to bet the house on it, right? You wouldn't want to do that. Probably wouldn't want to bet your house on much. That's true. Okay. It's pretty easy to convert odds to probability and probability to odds. Okay. If the odds in favor of something are, let's look at this one. The odds in favor of getting a queen. So we know the probability is 4 for 2. That's what we're looking for. Okay. The odds in favor of getting a queen are 1 to 12. Okay. Well, what did we say about 1 plus 12? Yeah, thank you. It's 13. Yes. We said that the odds of the the probability, the one on the bottom and the one on the top. Well, if you look at it this way, one on the bottom, the one in the numerator and the denominator add together to give you the total sample space. So for a queen, right, the sample space is now 13, right? And the numerator is what you're looking for the probability, right? So the event is 1. So 1 out of 13 is the probability of getting a queen. Okay, so all you do to go from odds to probability, you add the top and the bottom, and then you put the top one over that number. Pretty easy. So if we said that, again, a horse race, 5 to 8 odds in favor, the 5 to 8 odds. 5 to 8 odds in favor of that horse. Okay, if we want to figure the probability of that, okay, what do? 5 plus 8 is the denominator, right? And the numerator is just the 5. So 5/13, okay, which is whatever that ends up being. Okay, less than 50%. Okay, let's do another example here. If something is 1 to 1 odds, what's the probability of you winning? It's 0.5, right? 1 to 1 is 2, and then put the 1 on the denominator. 1/2 is the probability, right? So probability of the event happening is 1 to 1. Or sorry, 1/2 or 50%. Okay, so 1 to 1 odds is, even odds, as they say. Questions on that? Okay. All right. So that's the beginning of probability. Next time tomorrow we're actually going to talk about conditional probability, which means that if something happens and something else has already happened that's related to it, we can cancel out some of the probability. So we're going to figure that out. All right.